A hidden world 5 Earth masses may haunt our outskirts. If it exists, it explains weird orbits we already track. Tonight, we follow the clues and see where it hides. The immediate takeaway is simple: our map might be missing a planet. Let's look for Planet 9, without a spaceship, just gravity. Far beyond Neptune, sunlight is a thin blue whisper. Out there, Planet 9 is the proposed missing heavyweight. It's defined as a large planet beyond Neptune, orbiting distantly. People care because its gravity could tidy chaotic outer orbits. The claim rises from clustered paths of distant icy bodies. Those paths point one way, like iron filings around a magnet. A hidden mass could herd them and keep their tilts aligned. Gravity does this by trading energy and angular momentum over time. Each close approach shifts direction slightly, then repeats for millennia. The net effect is shepherding, not smashing things to bits. In 2016, 2 researchers outlined this pattern with 6 outliers. They modeled a planet between 5 and 10 Earth masses. Its orbit stretched perhaps 400 to 800 AU. 1 AU is Earth's distance from the Sun, about 150 million kilometers. It would also be dim, with a dark, possibly icy surface. Example in real terms, 12 extreme objects now show similar clustering. Their perihelia sit beyond 250 AU, and their angles bunch together. Simulations matching that behavior tend to require a hefty perturber. So the picture is simple: a heavyweight could be hiding far out. Picture orbits as stretched rubber bands around a dim campfire. Apsidal alignment means their long axes point roughly the same way. That alignment matters because random tugs should smear directions over time. A distant planet can imprint order through slow, repeating nudges. It trades angular momentum and locks the orbits into safer paths. Sometimes it flips them slightly above or below the main plane. That tilt pattern is another clue, paired with the apses. Mechanically, think of resonances where periods relate by simple ratios. In resonance, small pushes accumulate and the effect becomes noticeable. No collisions here, just gradual steering over millions of years. Take the extreme trans-Neptunian objects with perihelia beyond 250 AU. Several cluster within about 30 degrees of one another. Their longitudes of perihelion differ, yet they avoid pointing at Neptune. Simulations with a 5 Earth mass planet reproduce that avoidance pattern. Place it near 500 AU with an eccentric, inclined path. Its period would run around 10,000 years or more. Over each cycle, the test particles precess but keep antialigned. Antialigned means their closest approach points roughly opposite the planet. That configuration prevents disastrous encounters and keeps them long-lived. Researchers count survival times that exceed 1 billion years. Example numbers: one model matched 12 objects without overproducing scatter. Bottom line, the mechanics allow order to emerge from weak pulls. Now skeptics asked a blunt question: could bias fake the pattern? Bias here means surveys favored certain sky patches and distances. That definition matters because missed objects won't reveal true distributions. If telescopes looked mostly near certain longitudes, clustering appears. Teams have modeled real survey footprints and injected fake objects. Often, some clustering remains, but not as strong as observed. Another idea replaces Planet 9 with a broad, massive debris disk. A disk of countless small bodies could tug collectively, like syrup. Collective gravity would smooth the orbits and mimic ordered tilts. But you need a lot of mass, several Earth masses spread wide. Thermal data and dynamics limit such a disk, though not completely. Neptune's past migration offers a third path, sculpting before freezing. As Neptune moved outward, resonances trapped objects and shaped alignments. That process helps, yet struggles with the most distant cases. A passing star long ago could also twist the outer architecture. Close flybys are rare and timing must be exquisitely tuned. Example comparison: bias-only models match roughly half the alignment strength. Add a debris disk, results improve, yet require hefty mass. With a planet, matches reach within uncertainties for current samples. So the trade-off stands: simplicity versus parsimony in ingredients. Net result: alternatives exist, but the planetary option remains competitive. So where could a cold giant hide in plain sight? Semimajor axis means the orbit's average size over time. Predictions land between 400 and 800 AU for that measure. Eccentricity likely sits moderate, maybe between 0.2 and 0.6. Inclination could tilt 15 to 30 degrees off our plane. That matters because sky position and speed depend on these. Near aphelion, it crawls and blends into crowded starfields. Observationally, the Milky Way's clutter is the worst background. Brightness depends on size, distance, and a reflective surface. A 5 Earth mass mini-Neptune might span 2 to 3 Earth radii. With albedo near 0.3, visual magnitude could hit around 23. At 600 AU, that is telescope hard, but absolutely detectable. Motion is the giveaway, a few arcseconds per hour at most. Cameras shoot repeated frames, then subtract, leaving moving dots. Parallax across nights helps because stars barely shift at all. Infrared can help, though such a world would be frigid. Thermal brightness would be faint, near instrument sensitivity limits. So survey strategy targets speed, not heat, across huge areas. Example numbers: one search covered thousands of square degrees with depth. It recovered hundreds of known rocks, yet no obvious heavyweight. Net result: the likely hideout is slow, faint, and crowded. That triad explains the difficulty, without requiring magic camouflage. Here is how the hunt actually works on modern skies. Wide cameras scan swaths, then algorithms sift frames for movers. The basic idea is simple: linked dots that shift consistently. Consistency matters because noise and asteroids clutter every exposure. Subaru's Hyper Subprime Cam excels here, with enormous, sharp coverage. Teams take several shots per night, then repeat on later nights. They difference images, flag suspects, and test parallax tracks. Parallax gives Earth a built-in baseline, perfect for slow travelers. Zwicky Transient Facility adds cadence, hammering the sky nightly. It favors speed, catching movers that many surveys might miss. WISE scanned in infrared, delivering another angle on cold giants. It places limits by failing to see a warm Neptune. Machine learning now filters artifacts and ranks the candidates. Human eyes still check, because weirdness can fool even careful code. Follow up with bigger scopes nails down motion and color. Color hints composition, while motion confirms a distant orbit. Rule of thumb: real planets keep steady paths across weeks. Examples abound. Surveys rediscover Pluto nightly, proving pipelines work. They also snag comets and dozens of distant, extreme objects. One project scanned 14,000 square degrees to magnitude 22. Another reached deeper, hitting 24th magnitude across smaller tiles. Bottom line: the net is wide and the checks are strict. Each season expands coverage, while software grows more patient. Every missed patch shrinks and the map tightens around targets. Non-detections still speak, and they squeeze the possibilities hard. Radio ranging to Cassini constrained big tugs in Saturn's neighborhood. That means no Jupiter-sized intruder skulking a few hundred AU. Numbers-wise, disturbances beyond tens of meters stayed undetected. Thermal scans from WISE ruled out a warm, Neptune-sized body. A cold mini-Neptune remains allowed, especially far from the sun. Stellar occultation surveys watch stars blink when objects pass. They haven't reported a giant shade that far out, but the sky coverage is tiny and blinks are brief. Microlensing limits weigh on exotic options, like a tiny black hole. A primordial black hole could mimic mass but lack reflected light. Surveys like Ogle constrain such masses, yet windows still exist. Gravitational focusing would betray it through rare, short brightenings. Searches find few, placing bounds near Earth mass to Jupiter mass. Closer to home, clustering statistics have grown and relaxed slightly. Adding objects softens the signal, yet it continues to persist. Example constraints: regions near the galactic plane remain hardest to probe. Other regions have been scoured to about magnitude 24. So probability mass migrates towards slower, dimmer, trickier corners. What to remember: null results prune branches, but not the trunk. The next chapter belongs to a telescope in Chile's desert. Rubin Observatory will film the sky night after night. Its camera is huge, delivering rich, deep, wide snapshots. Depth matters here because Planet 9 would be faint. Cadence matters too, because faint things still move slowly. Algorithms will stitch motion across months, using parallax and color. Simulations suggest Rubin can see down to magnitude 24 or deeper. Translate that: a 5 Earth mass mini-Neptune at 700 AU. Citizen scientists can help, checking oddities that slip past. Fresh pipelines test difference imaging and smarter artifact rejection. Cross-matching with infrared catalogs will isolate unusual colors. A real candidate should be neutral to slightly blue, probably. Its motion should be smooth and consistent with orbital predictions. Follow-up spectroscopy could sniff methane or hazes if reflected light cooperates. If we find it, mass and radius reveal its nature. A dense super-Earth tells one story, a puffy mini-Neptune another. Either way, formation models shift and solar system history rewrites. If we don't, constraints will sharpen and alternative models strengthen. Example forecast: within 5 years the search volume could triple. Bottom line, discovery or denial, we learn how our outskirts work. That shadowed giant might exist, or the pattern might fade. Either outcome cleans our map and tightens our physics. I love that gravity leaves clues, even in near darkness. If a planet waits out there, the sky will confess. If not, we've tamed bias and uncovered new dynamics. Want updates when the next clue appears? Subscribe for more. Thanks for exploring the cold fringe with me tonight.